Welcome to this essential guide for Unity beginners, where we'll explore the powerful yet often misunderstood world of coroutines and the Unity main thread. Understanding these concepts is crucial for developing responsive and performant applications in Unity, especially as your projects grow in complexity. Coroutines in Unity offer a unique way to execute code over multiple frames, allowing you to pause execution and resume it later without blocking the entire application. This asynchronous-like behavior is a cornerstone for many dynamic game mechanics and user experiences. Unlike regular functions that run to completion in a single frame, coroutines can delay actions, wait for events, or queue operations, making them ideal for animations, sequencing complex events, and handling operations that span several frames. They provide a more structured approach to time-based logic compared to traditional update loops. To initiate a coroutine, you typically use the start coroutine method, passing in the IEnumerator method you wish to run. The yield return statement is crucial for pausing its execution, allowing Unity to process other tasks before returning to the coroutine at the next frame or after a specified condition is met. However, it's vital to understand that Unity primarily operates on a single thread, known as the main thread. This main thread is responsible for orchestrating almost everything that happens in your game, from rendering graphics to processing user input. All Unity API calls, including UI updates, modifications to game objects, physics calculations, and input handling, must occur on this main thread. This design choice simplifies development but also introduces specific performance considerations. If the main thread becomes blocked by a long-running operation, the entire application will become unresponsive, leading to noticeable freezes, stuttering, and a poor user experience. This is a critical issue to avoid in any interactive application. This brings us to the core limitation. Despite their ability to pause, coroutines still execute on the main thread. They don't magically move work to a separate background thread. They simply allow you to spread a single task across multiple frames on the main thread. Therefore, if a coroutine performs a heavy, synchronous, or blocking operation that takes a significant amount of time within a single frame, it will inevitably block the main thread, causing the UI to freeze and the application to become unresponsive until that operation completes. Let's demonstrate this limitation by creating a blocking coroutine in Visual Studio. We will write a script that intentionally performs a computationally intensive task to observe its impact on the Unity application's responsiveness. We'll start by defining a class blocking coroutine that inherits from monobehavior and includes a start method. This is the standard setup for any script that needs to interact with Unity's lifecycle events. Inside the start method, which is called once when the script instance is being loaded, we'll call start coroutine to begin our perform task coroutine. This initiates the execution of our potentially blocking operation. Now, let's define the perform task coroutine itself, which must return IEnumerator. This return type is essential for Unity to manage the coroutine's execution across multiple frames. We'll add a debug log message to indicate clearly when the coroutine begins its execution. This will help us track the flow of our script in the Unity console. To simulate a heavy, blocking operation, we'll use a while loop that runs for approximately 5 seconds. This loop will continuously execute a demanding calculation, preventing the main thread from doing other work. Inside this while loop, we'll perform a computationally intensive task, such as a nested for loop iterating 1,000,000 times, calculating math, sqrt for each iteration. This type of operation is designed to consume significant CPU time. Crucially, notice there's no yield return statement within this heavy calculation loop. This is what makes it blocking. Without a yield return, the loop will execute entirely within a single frame, monopolizing the main thread. Another debug log will be placed inside the while loop to confirm the coroutine is still working, displaying the calculated value. This helps us see the progress of the blocking operation in the console. Finally, after the heavy task completes, we'll log that the coroutine has finished and include a yield return null to properly end it. This yield return null signals to Unity that the coroutine has completed its execution. Now, with our blocking coroutine script ready, let's switch to the Unity engine to see this script in action and observe its impact on the application's responsiveness. we'll attach our blocking coroutine script to a new game object in the scene. This will ensure that the start method of our script is called when the game begins, initiating our coroutine. For our demonstration, we'll add a simple UI element, like a button, to the scene. This button will serve as a clear visual indicator of whether the UI is responsive or frozen during our test. This button will serve as our visual indicator of UI responsiveness. If the button becomes unresponsive or unclickable, it clearly shows that the main thread is blocked and cannot process user input. Now, when we run the scene, observe what happens to the UI button. Pay close attention to its interactive state and any visual feedback it provides when you attempt to click it. As the coroutine executes its heavy task, you'll notice the button becomes completely unresponsive. Attempts to click it will yield no visual feedback or action, demonstrating the main thread's blockage. The entire application freezes, and any animations or interactions will halt until the coroutine's blocking operation concludes. This clearly illustrates the detrimental effect of long-running synchronous tasks on the main thread. This clearly demonstrates that even though it's a coroutine, a synchronous heavy computation still locks up the main thread. The coroutine, despite its name, does not inherently provide multithreading capabilities. So why does this happen? The fundamental reason is that all Unity API calls and UI updates are strictly tied to the main thread. Unity's architecture requires these operations to be performed sequentially on this single thread. When our coroutine is busy with its intensive calculation, it monopolizes the main thread, preventing it from processing other crucial tasks. It essentially holds the main thread hostage until its heavy work is done. This includes rendering new frames, handling user input, and updating any UI elements, leading to the observed freeze. The main thread simply cannot get to these other tasks while the blocking operation is underway. To avoid these freezes and maintain a responsive application, we need to offload heavy computations from the main thread to separate background threads. This allows the main thread to continue its essential work without interruption. The C# Task Parallel Library, or TPL, provides an excellent solution for this. It offers a robust framework for asynchronous and parallel programming, making it easier to manage background operations. TPL allows you to easily move computationally intensive tasks to background threads, freeing up the main thread to continue rendering and handling input. This significantly improves application responsiveness and user experience. Let's look at an example of how to implement this using Task, run within a coroutine. We'll create a new script, non-blocking coroutine, to demonstrate this improved approach. Our Do Something Long coroutine will now initiate a new task using Task, Run. This Task, Run method is key as it executes the provided action on a thread pool thread, effectively moving the heavy work off the main thread. Inside Task, Run, we'll call a long operation method, which simulates our heavy computation. For demonstration purposes, this long operation will simply put the background thread to sleep for a few seconds. Crucially, this long operation now runs on a separate thread, ensuring the main thread remains responsive. While the background task is running, the main thread is free to update the UI and process input. We use a bool task completed flag and yield return new wait until to wait for the background task to finish. This allows the coroutine to pause until the background work is done, without blocking the main thread. However, if you need to update Unity UI or game objects after a background task, you cannot do it directly from the background thread. Attempting to do so will result in errors, as Unity's API is not thread-safe outside the main thread. This is where a dispatcher comes in. A dispatcher allows you to queue actions to be executed safely back on the main thread. It acts as a bridge, ensuring all Unity-specific operations happen in the correct context. Let's create a simple Unity main thread dispatcher class. This class will be a mono behavior that lives in our scene and provides a mechanism to execute code on the main thread from any other thread. This class will use a concurrent queue to store actions that need to be executed on the main thread. The concurrent queue is a thread-safe collection, allowing multiple threads to add actions without conflicts. The inQueue method adds an action to this queue. Any background thread can call this static method to submit a piece of code that needs to run on Unity's main thread. In the update method of our dispatcher, which runs on the main thread every frame, will continuously dequeue and invoke any pending actions. This ensures that queued actions are processed promptly and safely. To use it, from your background task, you would call a Unity main thread dispatcher in queue with the main thread UI code. This pattern ensures that all UI updates or game object modifications are properly marshaled back to the main thread. This ensures that any Unity-specific operations, like updating a UI text or changing a game object's position, happen safely on the main thread. The dispatcher effectively prevents cross-thread access issues. For even more performance-critical, data-oriented tasks, Unity's job system offers another powerful multithreading solution. It's designed for scenarios where you need to process large amounts of data in parallel. It's designed for highly optimized, burst-compiled code, making it suitable for complex calculations on large data sets, such as those found in simulations, procedural generation, or AI pathfinding. The job system provides a safer and more performant way to handle these types of tasks. In summary, coroutines are powerful for sequential operations, but run on the main thread. They are excellent for spreading tasks over multiple frames, but do not inherently provide multithreading. Long-running synchronous tasks within coroutines will freeze your UI and make your application unresponsive. This is a critical pitfall to avoid, as it severely degrades the user experience. To prevent this, offload heavy computations to background threads using the C# task parallel library. This allows your main thread to remain free and responsive, ensuring smooth gameplay and UI interactions. Always use a dispatcher to safely update Unity objects and UI elements from these background threads back on the main thread. This is a crucial step to avoid errors and maintain the integrity of your Unity application. And for highly optimized, data-intensive tasks, consider exploring Unity's job system. It offers a robust and performant solution for parallelizing complex calculations on large datasets, pushing the boundaries of what your game can achieve. By understanding these limitations and applying these best practices, you can create more responsive and performant Unity applications. Mastering these concepts will significantly improve the quality and stability of your games. Thank you for watching, and happy coding! We hope this guide has provided you with valuable insights into managing coroutines and the Unity main thread effectively.